So you're here, so you probably want to know how this square could be a circle for some metric and some center. If you don't know what I'm talking about, you should go ahead and watch the first part, where I went over some of the background, what a metric is, and posed the question itself. It's linked up in the cards over here. Okay, so you're still here, so let's go ahead and start. First off, we're going to go through this in 3 parts. The first part is going to be how we think about points. Second is what metric are we using, and third we'll go over the center and the radius. So it's gonna build up to the answer, so I won't give it all away at once. If you want to think about things in between sections, that's a good idea if you still haven't figured it out. Let's talk about how we're going to think about points in the unit square. We're going to use their binary expansions, and we're going to avoid repeating ones. I talked about this before in another video that's also linked up above, and I linked it in the last video as one of the hint videos, but quick refresher. The binary expansion of a half is 0.1, the binary expansion of a fourth is 0.01, and the binary expansion of an eighth is 0.001. For uglier numbers, like let's say 0.01101 in binary, we can convert this back to a fraction by summing up a fourth, an eighth, and a 32nd, since there is a 1 in the second, third, and fifth positions. Now in the coordinate grid, we can think about these expansions as putting numbers into bins based on how their expansions start. So the numbers with an expansion starting with 0 come before a half, and the ones starting with a 1 in their expansion come after a half. And we can continue breaking the interval on half like this to get finer and finer bins. We can also do this on the other axis as well. And so taking those two things together, we get a visual of where points with certain expansions lie in the grid. So now that we've set up how we're thinking about points in this space, let's talk about the second part of this video, which is what metric are we using? We're going to be using a variation of a symbolic metric, and you're probably wondering what a symbolic metric is, so here we go. Take 2 strings of symbols and look at how many symbols that these 2 strings match on, starting at the beginning of the string. The distance is 1 over p to the k, where k is the length of the largest block of symbols that the 2 strings agree on, where the block starts at the first symbol, and p is some positive integer. I'm using p here because we're going to be using primes to get our metric to work out and give the circle that we want. So as a quick example, let's go ahead and take p equals 2, and let's look at the strings 0 repeating and the string 00010 repeating. Notice that they agree on the first 3 symbols and then disagree on the 4th one. So the distance will be 1 over 2 to the 3rd, or an eighth. For the purposes of this video, I'm not going to go into the proof of why this is a metric. And if you're wondering what a metric is, I talked about that in the part 1 of this video. However, a few of the properties are pretty intuitive, like non-negativity. It's a good exercise to go ahead and double check that this is actually a metric. And if you decide to tackle it, remember that within our context, we're not allowing repeating ones. But generally, with a symbolic metric, that may not be the case. This is great for symbolic versions of points on the line, because we can take the binary expansion and compare them directly. But we're working in the unit square, so we're gonna have to do some work because each point comes with 2 pieces of information, or 2 strings attached to it that give its location. In order to remedy this, we're gonna go ahead and build a new metric using the sum of 2 symbolic metrics. The first one will operate on the x coordinate and will be 1 over 2 to the k. And the latter will be the metric that operates on y coordinates and will be 1 over 3 to the l, where k and l are just those lengths of the blocks of agreement as they were in our original symbolic metric. The argument that a metric defined by the sum of 2 coordinate metrics is a metric follows pretty quickly from the fact that the 2 things that you're summing together are actually metrics. This is another thing that you should definitely think about if you have the time, but I'll go ahead and get into the triangle inequality. In order to show the triangle inequality, use the fact that the triangle inequality holds for both of the coordinate metrics that you are summing together. And with a bit of rearrangement, you get the inequality to arise. The other properties, again, are a bit quicker and Again, you should definitely spend some time thinking about it if you want to have a better understanding of what's going on here. So we have our metric. Let's go ahead and do an example just to see how it works. So if we want to see how far apart the point A equals 1/2 1/3 and B equals 33 64ths and 5 16ths are, we can express them in binary to get A equals 0.1, 0.01 repeating, and B equals 0.10001 and 0.0101. Then we apply the coordinate metrics, and you sum up the results to get 1/2 to the 5th plus 1/3 to the 5th, which is 275 over 7,776. Now that might look like a mess, but it's not as bad as it seems. Okay, so we've gone over how to think about points in the space, and you have the metric now. The only thing left to figure out is where is the center of the circle and how large is our radius. If you want to try and figure it out for yourself, you should go ahead and pause here. Alrighty, so let's go ahead and just give out the radius. It's 13/36, and the center A will be 1/8 1/8. In binary, 1/8 is just 0.001, so we can express A like so. And by using a bit of factorization of the denominator of the radius, we get 4 times 9, which is just 2 squared times 3 squared. And noticing that 13 is just 4 plus 9, we can rewrite the given radius in the form of 1/2 squared plus 1/3 squared. This is exactly in the form that our metric would compute out to, because the coordinate metric in the x direction is 1/2 to the k for some k, and the coordinate metric in the y direction is 1/3 to the l for some l, right? This tells us that in the x direction, we need to agree on the first 2 blocks, and no more, no less. And in the y direction, we need to do the same thing. Our choice of primes also forces it so that we can't agree more in one and less in the other and get the same distance out as if we agreed in exactly 2 places in both coordinates. And that's another thing you should go ahead and check. But anyway, with this information, we can figure out that since the binary expansion of 1/8 is 0.001, we need our points in the circle to have binary expansions that start with 0.000 in both coordinates. If we go back to the idea of binning the coordinates on the grid, we can figure out where the 0.00 bin is. And those will give us all of the points that have 0.000 at the beginning of their expansion. So all of the points in the 0.000 bin will agree with our center at the first 2 places in each coordinate. And so these are exactly the points on our circle. So we got the circle was a square and a filled in one at that, which is kind of cool. I mentioned that the borders might be a bit odd to think about at the end of the last video, but the ones that fall on the lines x equals 1/8 and y equals 1/8 are excluded from the square, while the ones that lie on lines x equals 0 and y equals 0 are included. This is because on the 1/8 borders, you have one coordinate that matches everywhere, and so the distance is too small to be equal to the radius, and therefore you're not on the circle, you're inside of it. Which is a weird thing to think about too, because you're on the border of this thing that's already filled in and you're inside of it. Anyway, not important, but just another thing to think about, right? With all of these pieces, you might also want to think about different ways you could have formulated this metric using this symbolic idea. When I first started formulating this problem and putting together the first part of this video, I was trying to get a square out with the metrics that I was making, and I ended up getting L-shaped circles. So if you want to take some time and try to figure out how I got those, that might be fun. The cool thing though is that once you figure out how the square circle works and what's going on with the metric there, you can actually mess with the metric even more, and you can get disjoint squares as being in the same circle. And so that's kind of the challenge, is like if you can do that, you actually have a pretty good grasp of how these things work, I would say. That's all I have for you today. I'm sorry this went up late, but I'm happy to be back at this again. Hopefully I will have another video out sooner rather than later. If you enjoyed this video, give it a thumbs up and subscribe for more mathematics videos. As always, I am Nathan, this is Chalk, and I will see you next time.